the 256 qubit system that we have outlined for next year. So this system is going to be something that's substantially more powerful than any other quantum computer out there. So we can do something for low tens of millions that our competitors need billions of dollars worth of parts for. And that's just an incredible advantage, a structural advantage in any new market. I really fundamentally don't believe there's anything unique about the human experience versus any other complex system. So I'm an optimist that humanity will find a way to become better and stronger, as it has done over the last thousands of generations.
Hi, and welcome to another episode of the Quantum Economy Podcast. Today I'm joined by Chris Ballance, co-founder and CEO of Oxford Ionics. Chris is a physicist turned entrepreneur. He started out at the labs at Oxford and ended up creating record-breaking qubits and a company that was recently acquired by IonQ for more than $1 billion. Chris and I talk about why error correction might not be the ultimate solution. And we look at the business side of quantum, from unit economics to the challenge of scaling a deep tech company, taking it to a real market. Also this week, we take a look at some philosophical questions, and Chris shares his thoughts on why optimism still matters and why humanity, as he puts it, will always find a way forward. This is the Quantum Economy Podcast and my conversation with Chris Ballance. I was thinking about this when I was reading up on your approach and some of the things I've been thinking about lately. What if we got the whole aspect of error correction wrong? How about we start with an initial condition of error-free qubits or some kind of error-protected state? And I wanted to pick your mind a little bit about that in terms of your experience in physics and how you look at quantum physics as we have grown, from the theoretical foundation to now building scalable quantum computers. So what are your thoughts on, I think is there an approach that we could look at error-free qubits?
I think that's a great question. I think a lot of people look at quantum error correction as a magic bullet that can solve all ills. And it's not. It's a software solution to a hardware problem. By far the best way of solving any issue in quantum computing is having error-free qubits. And you can't have error-free qubits in the same ways you can't have error-free classical computers. But you can definitely strive to have the best hardware possible before you start adding quantum error correction. And it turns out when you work through the maths on this, even just getting your qubits an order of magnitude or two lower error than conventional approaches, if you can do that, I wouldn't say the challenge of scaling goes away, but you're suddenly looking at a way different problem. If you look at conventional qubits right now, the industry average error rates, you need somewhere like 10,000 to 100,000 physical qubits just to make one logical qubit. With just a 1 or 2 order of magnitude improvement in your qubits, you can get this down way closer to 1 in 10. And that, when you say it in the abstract, doesn't sound too different, but this is an amazing difference in how fast you can scale your technology platform. And if we look at this means we can be solving industrial scale applications with a low error technology and with the same physical number of qubits, so the same cost of device, the same physical scale. You can have something that just doesn't work at all if you're doing this with worse error qubits.
So when you went about, you obviously you chose, or you came out of the theoretical foundation with a conviction that trapped ions is like the technology or the approach to quantum computer that you are probably, in your world, sure that this is the way to go about. Can you just elaborate a little bit why, your background when you spun it out of Oxford and why you chose to look at this approach as the most promising path to build a scalable quantum computer?
So before I started out in trapped ions, I actually worked in some silicon vacancy center work. So working on stuff that wasn't trapped ions. And what I learned from that is that there was some fascinating science to do. But I mean that in a pejorative sense. There really was a lot of uncertainty in how you can even build these things reliably. And what that taught me is that you really don't want to be doing science on your qubits. You want to be having qubits that work. And then the interesting science is how you put these things together to make large-scale computers. And this is also what we learned from classical computer science. Computers really took off, not with people trying to understand how to build better transistors, but when people said, right, we can build these transistors and they just work. Now, how can we put a large number of them together in order to make large-scale systems, and how do you learn the lessons from actually scaling out that technology? And what I found when I went into trapped ions is that it was very clear this was a technology that could allow us to engineer very low error rates. So build fundamentally very good hardware, because you want to make good hardware and then build your software on top of that, rather than use software to solve problems in hardware. And, very early on, back in the 2010, 2012, I demonstrated the world record performance in any quantum technology using trapped ion qubits. And from that, I learned, with these systems, you really can engineer them this well, and you really can control these errors and understand where they're coming from and just systematically work through reducing these error rates. What I also learned from that, back then, using lasers, is that lasers are a very difficult technology to scale, using lasers to control the qubits. And that sent me off on, 5 years in the Wilderland, trying to work out how we could have the beauty and the power of trapped ion qubits without all of the pain that lasers get you in terms of scaling. And this is when my co-founder Tom and I found this electronic qubit control. And it became very clear that you could use electronics to control qubits. And the really interesting thing about it is that it made building the first device way harder than with lasers. With lasers, you can knock up a lab, lock up a system, and start getting them working in 6 months to a year. To get this working with electronics took us 5 years of blood, sweat, and tears trying to work out how to build out these chips, how to integrate all the elements into a chip to make it work. So the cost of getting just one kind of pair of qubits working was really massive. But what was really important, and the vision behind this, was that once you had the technology working on a pair of qubits, adding more qubits, building out larger devices, was now building out larger and larger chips. Everything to control the qubits could be built into a chip. Because ultimately it's electronics, and we know how to scale electronics. And this is, what I spent 5 years of my career on in academia. And then once we started being very clear at work, I had the first real hard crunchy data showing that you could hit world record performance using this electronic control rather than lasers. That's when I started Oxford Ionics back in 2019.
So you think that like superconducting qubits with the scalability of cryogenics, that's a topic that is much harder to solve? Or if you look at like PSI quantum and photonics, that these approaches aren't they're more challenging to scale? Is that something that you like, because you said you've looked at various other approaches, right? So would you say that you think you are in a more promising land in terms of scaling then?
So I think you can answer that emotionally or logically. Emotionally, yes, absolutely. Otherwise, I wouldn't be here doing this. I'll be working on the technology I believe is the most scalable.
That is an obvious stress.
But then technically, we can start analyzing what the hard points are. And philosophically, I have a firm belief, just based on observations of other technology revolutions, that technologies, any new product, any new way of putting together technology can either, solve a new problem that no one's ever solved before, and that's quantum computing. And it has to use, to be successful, pretty much off-the-shelf components that already exist. Or you can engineer completely new components to solve existing problems in existing markets. If you're trying to use a new technology, a new way of doing things in order to solve a new problem, you have a lot of horsemen of the apocalypse circling your business model. And the great thing about trapped ion platforms is that we use atomic physics. This has been known since the very early 1900s, right? We know how atomic physics works. It works incredibly reliably. That's why we make atomic clocks out of atoms. We're then using chips, and the kind of chips we use, the metal structures we use, aren't novel. In terms of the fabrication, we could have built them in a semiconductor foundry at the turn of the century. And then we have electronics around this. Again, this is not state-of-the-art in any one technology aspect. So what this means is we're taking loads of things that already exist, and where people have already invested lots of money building out the supply chains to make them work, and where people in industry already know how to turn these into robust products. And we're putting these together in a new way to make quantum computers. And there's really no quantum platform out there that has as many things going for it as trapped ions. If you look at, say, a photonic platform, you can sketch out something and say it looks like conventional chips, but you find yourself having to do material science and introducing new materials into foundries that people can't make. Or doing things where you say, well, I just need to get 3 or 4 orders of magnitude improvement in raw device performance over what TSMC or global foundries are currently doing. when you stack together all of the different things there, that's pretty scary. If you look at superconducting qubits, you can say, well, they look like chips, they just have to be cold. But first of all, they have to be at millikelvin temperatures. And when you start looking at just the resource consumption of scaling this up, you start going into completely unknown supply chains where you can do a thermodynamics calculation and say, well, the rules of thermodynamics don't say my machine is impossible to build, which is a necessary but not sufficient condition for commercial success.
Right.
Or you can look at the precision you should need to fabricate these devices, which becomes way better, way more precise than, Intel's, several nanometer fab, which they've been struggling for over 5 years to get up and running and commercialized. And you look at all of these things and say they're fundamentally different problems. In ion trap systems, we're working fundamentally with engineering problems. It doesn't mean it's easy, right? It takes blood, sweat, tears, and capital to make these things work, and incredible passion from lots of dedicated people. But what it means is you have the conditions for success. You can find the right people who have commercialized each of the different elements in the device. And then it's a matter of organizing them together, working towards one common vision to go implement it.
I want to get to that point of new materials and material design and coming out of some quantum AI algorithms that there could be actual creation. I want to get back to that topic, but I just want to have you looked at NV centers as an approach?
Yeah, so I know a lot of people working across all the different technologies,
right?
And I think NV centers make great science projects.
Mm-hmm.
They make incredibly good sensors. Which is, I think, where we're going to see a lot of value unlocked from NV centers.
For communication and sensing.
Exactly. I don't think they make great quantum computers because of the challenge of putting lots of them together and getting them to talk.
But if you could do that, though, I mean, if you could find ways to, combine them into scalable chip production, that could be a room temperature scalable quantum computer, right? In theory.
But potentially, there's a lot of ifs there. Ultimately, I see a lot of analogies between between NV centers and between ion trap systems. Like ultimately, in an NV center, you have a vacancy, which basically behaves like an isolated atom, just happens to be built into a lattice of material. And with an ion, you have an individual atom that just happens to be hanging in vacuum. Ultimately, if you look at the physics involved, if you have an atom that's like in an ion trap that sits some tens of microns away from the surface, it really is like an individual atom just hanging in a void. It's guaranteed perfect. If you look at a vacancy inside a crystal structure, you depend a lot on the crystal structure and the properties around it. So ultimately in these systems, it's way easier to get, an individual isolated ion working. And, we've built devices that hit world record performance with room temperature operation. And people have even built ion traps that work at a few hundred degrees centigrade, right? So you can put these things in an oven and make them work. I don't think that's necessarily the approach we need to get to for the next 5 or 10 years, where I think a lot of the value unlock is building systems with really good unit economics and getting first to market. But when we need to start miniaturizing, when we need to start compactifying and cost reducing, there's very clear engineering pathways to do that with trapped ions. And I just really don't think that's the case with any other technology out there for large scale compute. If you want to build a 5 or 10 qubit node, for example, as part of a communication network, maybe NV centers will look good for that. But I'd also say right now, ion trap systems outperform them for all the meaningful tasks, including communication.
But I liked your bridge there. I liked, you said that because in my layman term as a non-physicist, that was kind of sort of where I was heading. So it was very interesting to get your take on that. And it's wonderful to listen to how you resonate to these various technologies. And it just kind of sort of shows me how you have detached yourself from what is not, to understanding various approaches, and then concluding kind of sort of where to head with this. So,
right.
So that's
ultimately one of the things that the way I like to tell my team internally on this is that you can have the best performance and technology that scales. That's the entry ticket to the market. After you've got that entry ticket, the way anyone actually wins on markets is by unit economics. Ultimately, if you can sell something way cheaper and build something way cheaper than anyone else, that cost is a measure of complexity. So it both enables your customers to adopt it or gives you a better, stronger pricing power in the market. But at the same time, it is just a measure of the fundamental complexity of something, and building something for lower cost really means it's fundamentally simpler. And right now we're at the technology with this ion trap technology and electronic qubit control, where we have systems that are substantially cheaper to build than anything else out there. And what this really means is that we can build these systems faster, but also as we scale, the cost doesn't scale with the number of qubits. And we did some modeling on this that we made public a month or so ago, where we showed that for our 256 systems, we think we can do this with single-digit millions in BOM cost. Our competitor systems are tens of millions in BOM cost at least.
Yeah, wow.
It gets really interesting when you then look out a few generations, go all the way out to, say, a 2 million physical qubit device.
Right, yes.
We can do this with low double-digit millions of parts cost. And if you look at, say, a superconducting system estimate, even an optimistic one, the numbers are measured in the billions. So we can do something for low tens of millions that our competitors need billions of dollars worth of parts for. And that's just an incredible advantage, a structural advantage in any new market.
When you talk like that, I get like I'm listening to a private equity experienced investor looking at a new deep tech market, and and it's interesting. I would like to just get a little bit of an understanding of your journey as an Oxford physicist turned entrepreneur back in 2019, was it, that you set up the company, and now you're talking unit economics, you're talking scalability in a capitalistic term to say that, well, this is where it's heading. So just quickly take me through that journey, being at Oxford, spinning it out as a scientific endeavor, and then now looking at it from a strict market purpose sense. How has that shaped you, and what have you learned, and what are some thoughts about that journey?
So I've always been a bad physicist and a good engineer. So I wasn't sure entirely where I wanted to go when I took up and started a degree in physics at Oxford. But what was very clear when I started is that there weren't many people like me out there. There were lots of people, in my undergraduate course who liked getting the answers on the problem set right and then move on to the next problem. And I really, view that as the first step on the journey. I wanted to understand how to solve the problem, then I wanted to go do something with it. And, I finished my undergraduate degree. Wasn't clear what was best. I dipped my toes into professional software development and decided this felt very soulless to me, and I couldn't imagine spending my life doing this. And then I found quantum computing. And back in 2010, when I started in quantum computing, it was very clear that, first of all, this was something that was going to change the world. The most powerful form of computers that the laws of physics allow, if you can build that, if you can unlock the power from that, this is clearly going to be a meaningful theme of the next 20, 30 years. At the same time, it was also pretty clear that there were a lot of physicists working on it, and you needed to really understand the theory to make inroads on this. But this wasn't enough. There was lots of physicists working on things that, with my engineering hat on, I could see were clearly a dead end, where the physics might look elegant if you sketch it out on a whiteboard, but when you zoom out to a system engineering picture, it was clear you couldn't build these things. And I didn't quite have a language to describe this, but it was very clear that there were lots of people working on elegant dead ends and people getting lost in the elegance rather than understanding what kind of engineering problems they would need to solve to scale. And so it felt like a good time for me to join as someone who understood enough about engineering to at least be able to work out what questions to go ask the right kind of engineers to understand how hard these things were. And, being a good enough theoretical physicist that I could speak to the real experts in these topics and synthesize it together and understand where the real points are. And I found there are a few people who had the ability that I found I had to be a bit of a chameleon and to go fit in with the theoretical physicists, fit in with the engineers, fit in with the people who are actually building this stuff, fit in with the people in the workshop who understood how you could design for manufacture, and really put all of these things together to try and chart a path that they're kind of globally optimized between the best physics and the best manufacturability, rather than just optimizing for something you could engineer very well but wouldn't scale, or something that you could get really elegant physics on but have to hit completely new tolerancing on to make work at scale. And that's what started off my journey through this. And it's also what made me focus very much on some pretty unsexy themes at the time. Back in the early 2010s, mid 2010s, late 2010s, everyone was focused on getting a Nature paper showing they could do something on 7 qubits that was amazing, or push up to 23 qubits and run some sort of chemistry application. When at the same time, if you actually looked at the details, people are doing this in a way where they do heroic efforts to make something work, but it was very clear that to double the system size, to double the number of qubits, the technology they're using wouldn't work. And I found that distinctly uninteresting. Like, building small systems is only useful if it teaches you how to build large systems. And if you're going down dead ends to, collect things, gems, nature papers, but you knew it was a dead end, that just wasn't interesting to me. And I found that a pretty isolated environment. It turned out I was a good engineer and a bad physicist. And then as I started working out how we're actually going to commercialize this, what a path from saying, this is the right approach, how do we go make money with this? It then became clear that this was my home turf all along, and I'd just been just thought I was a physicist.
There is so much eloquently put and also so much play with there. I love that riff in that journey. And but it's interesting though how you experience these things, and it feels as if it's come upon you. It's just like you're not quite sure where the journey is going, but you kind of sort of start to figure out where it's not going. So you get into some fields and you just cut that out. What are the challenges then as a business person, as an entrepreneur? Is it the biggest challenge then to work the technology, the engineering part? Is it to get talent for scalability, or is it being the comedian or telling the story as you put it in the last couple of minutes? What are the things that you struggle the most with?
So I think the job of any leader in any sort of program or project or company is always simplifying, right? There's a whole amount of complex detail that everyone carries with them. And you have to find a way of picking out the essence and really communicating that to pull kind of a larger and more complex group of people along in the right direction at all points in time. And, ultimately the hardest part for me of quantum computing is that no one builds quantum computers right now. If you think of, say, the semiconductor industry now, people will go and do a degree in some sort of engineering and understand how computers work and understand how their specialized piece of technology fits into the big picture. And there are job titles, and everyone understands what the job titles are and what everyone's role is, to the point where you can recruit a team and get them up and running building a new type of chip pretty fast, since everyone has been in a company that builds chips. And the stuff they need to learn is just a little bit of detail about the specific technology that you're trying to commercialize. With quantum computing, that's not the case. We have to bring together a whole group of people that don't work together, that don't use the same language, and that don't know what the quantum computing market is going to look like, or how all these different pieces of technology go together, from software, from different aspects of hardware, from manufacture, from design, from quantum physics. So you really have to find a way of taking this group of people and putting them together fast and giving them a shared language that they can work out what part of the journey they're playing. And one of the things that I think is great about trapped ion systems is that these skill sets and these people already exist. So you're not having to create lots of these people from scratch, but it does mean taking a lot of people who've cut their teeth on building systems in academia and built up the skill set in academia, and then trying to teach them what is now possible working alongside a team of phenomenal engineers, rather than just what they could possibly do with a roll of duct tape and kind of an optics catalog manual, a year in a dungeon themselves on their own. And trying to get the idea of training into people of what kind of problems you can solve with a talented team of engineers fast, and what kind of problems are very hard because they end up serializing. So you have to just put 3 brilliant people on it for 3 years. That's an intuition that not many people have, and it takes a lot of work to build that and disseminate it amongst the company.
So that sounds like a visionary leader who is building a big company and has thought about this both from a technical standpoint and from an organizational standpoint. You talked about leadership and, being a founder and getting a team on board. And here comes a company that has also played with ion traps, a US company, and he says, Chris, hey, here's $1 billion. Why don't you join us and we buy you? And a UK company that in the midst of geopolitical tension, having IP structures, the battle of nation versus the battle of companies in the whole quantum space. And you say, like, here's $1 billion, or however much it was. I was like, why did IonQ need to buy you guys then?
So I've known the team behind IonQ for a very long time. I knew the academic founders of IonQ, Chris and Jungsang, well before IonQ was a thing. And obviously, when I met with the new CEO of IonQ, Nicolo, we had a nice chat. We said maybe there's something here, and then kind of moved on saying, well, it's probably not going to work. But, we kept on coming back and talking. And the more we talked, the more we realized that...
But just to get to you were competitors, more like perceived competitors, right?
Yeah.
Well, there's a beautiful story here. So that's what I want to get to. It's like you were competitors. I mean, my perception was these are two competitive companies that are kind of sort of in the same space. So that was the interesting part of it. So I just wanted to make that.
Absolutely. We're competitors, and competitors always talk, right? Not typically in the to emerge sense, but just the feeling each other out, like making sure you have good enough relations to understand. And what became very clear to me, obviously my first answer was no, we're going to stay independent, and we had a very nice Series B funding round lined up, about $130 million, to really go out and scale our quantum computers. And the stuff that was really keeping me up at night were things like, how do we scale out the technology platform and take it to an incredible core of a technology into a product that we can get out into a marketplace? It's how do we build up all the stuff we need around it to make a fully featured product offering? This is the go-to-market, the applications work, the engineering muscle, the production muscle. We had a pencil sketch of what we wanted to do here, and I was getting ready to spend a lot of money and a lot of time working out how we built that. At the same time, with IonQ, they had incredible teams that were already doing this. And what really became very exciting to Nicolo and myself as he started trying to work this out is looking at what we could do faster as we plug together IonQ's existing platform. They've been running systems on all the major cloud platforms. So hosting quantum computers and getting the battle scars from learning how to do this since before Oxford Ionics was founded. So there's incredible institutional knowledge and just teams built up to do all of this stuff fast. And when we started, working out together, literally on a napkin on a table, what we could do if we started putting these technologies together and putting the combined teams together, it became very clear that this was very exciting indeed, and ultimately could speed up both of our combined roadmaps over what we had individually. And what really sold me on this was just the business logic. When you look at all the stuff I've been dreaming of doing in terms of building really meaningful quantum computers and scaling them fast, it just became very clear that if we did this, if we, merged together, we could achieve something that was way more powerful than any of us could do in isolation. And that's pretty compelling, ultimately.
Yeah, because I think there's an important point there. I was looking at that. I think it's the AstraZeneca case, which is a very clear use case on, you have NVIDIA GPUs, want to strive for QPUs. You have the Amazon Web Services as a whole cloud service. And then you come in with domain knowledge in a very specific field from AstraZeneca. And then that's a very typical, path where you could see an industry, a use case to be scalable. And I think, obviously the first low-hanging fruits here are efficiency in terms of faster processing or energy, but there is something beyond that. So that I do really much understand, but I would also like to just, because I think there's an important part here also about the US, UK, the national aspect of securing intellectual property. So I think a part of the deal was you want to have some kind of Oxford substance in it. You want to have some UK ownership in that acquisition. Is that right?
So we have an incredible team here based in Oxford, which is where I am now. And this is always an important part of the deal. Ultimately, if you strip everything down, in any sort of new technology company, you're typically not buying the IP. The IP allows you to, when there is a steady, stable market, work out who has the upper hand. And that is, useful, but the real valuable thing is the people and the skill who can iterate fast and generate each new product release. Since the way we win in a market like this isn't by building something great and resting on our laurels, it's building the muscle, the engine that allows us to iterate consistently faster than anyone else in the market. So it's always about the people, the talent and the teams, and how you build out these structures. And it's very clear we had, across Oxford Ionics and across IonQ, incredibly skilled teams are doing this. So it become natural to say we're going to invest and double down and do more of this. So as part of the National Security Review, the UK government asked us to make sure we keep a mix of suitably skilled, qualified and experienced people to stay in Oxford. And, the answer to everyone on this is, well, this is a no-brainer. Obviously, we're going to do this. So it became a very easy constraint to come with, since our base case plan that kind of we underwrote for the business and issues of the deal already relied on us doing this and doubling down on it. So the structure we have now is based on what we want and what we think is best, which is aligned with the UK government and the US government's view on this as well.
Now that's a good way to see that collaboration working out. And I think in the whole tension path, to have this clear, the understanding of culture and people is obviously the fundamental. You trust in that, but also to have some playing rules to say that, this is how it's going to synergize, that I think that's very important in this technological winner takes all race, to have that sorted out. But I think also on that note, you had your timeline for scaling mapped out. There was a discussion on how to get enough logical qubits to actually do something useful in terms of business. How does that change now with the acquisition? Is that does the roadmap stay the same, or do you speed it up? Can you just elaborate a little bit on your roadmap? What do you see in the next 2, 3, 4, 5 years in terms of scalability, and if that has changed with the acquisition?
So what this deal allows us to do is to get products to market as a combined entity faster and to iterate on them faster. And to do this with lower organizational cost base, so with better unit economics. And ultimately, that's what really excites me. All of those things are leading indicators of being, winning the market, right? Of being in the right space to go ahead and do something no one else can do. So we've put out a public roadmap that outlines where we need to get to. But the really big watch point for me is the 256 qubit system that we have outlined for next year. So this system is going to be something that's substantially more powerful than any other quantum computer out there. And, it's easy to talk about this in the abstract and compare qubit counts and performance. The most powerful way I like looking at this is if you look at today's quantum computers, the most powerful systems out there, they're comparable in performance to the world's largest supercomputers. Which is nice, it's an exciting metric to look at.
In some scenarios, that is though. It's not
exactly. This is just in terms of raw mathematical power, and then you can look at pessimism factors when you apply this to different applications, and you can find certain types of applications where they beat supercomputers, certain applications where they're slower than supercomputers. The 256 qubit platform isn't just going to be more powerful in terms of raw compute fabric performance than the best supercomputer out there right now. It's going to be more powerful than the largest supercomputer that humanity will ever build. Right? Even assuming 1,000 years of technological progress based on what we know about the laws of physics, this next-gen compute platform, this 256 qubit platform, is going to be more powerful than anything. And you can extrapolate what it requires to work with out of GPUs. If you just take today's GPUs, you need about 10 to the power 20 NVIDIA H100s to compare raw compute power. So that's pretty impractical, but you can just look at the electrical consumption of all of this. The electricity consumption for this is something like 1 billion planet Earth's worth of power. Right? So this just gives an indication of just how impossible it is for any classical computer to reach this level of compute performance. It's just mind-blowing.
Yeah. Because this is always the argument to say that conventional GPUs have a lot of scaling potential. So if you have a new transistor that could work with the new NVIDIA chips, you could, make it 20x and reduce to 8% of the energy consumption. And there are many theories of things that are now going to be implemented and probably made commercial in a year or so. But here we're looking at a magnitude of efficiency that is way beyond what you can foresee with GPUs, CPUs, right?
That's exactly right. And you can say, well, maybe you get an order of magnitude. Maybe you get 5 orders of magnitude with GPUs. But you can you can't just scratch the gap there is between the fundamental difference between quantum and classical compute. And ultimately, that's what makes it so exciting. When you look at, coming back to unit economics, when you look at the fundamental economics of compute right today, it is electricity with a markup factor. If you look at the cost of using GPUs, you have the cost of the GPUs you depreciate over your lifetime. But a substantial part of the economics is the electricity these things use. We've heard about this, Microsoft buying 3 Mile Island to power data centers. If you want to go build a data center right now, you can buy the GPUs, you can find the space. The hardest thing to find is the power. So what this means is classical compute right now is basically a multiplicative factor on top of energy costs. When you look at what you can do with quantum computing, you can reduce the energy costs for given problems by factors of millions to billions. And when you put that together, what you say is that there is no way for classical compute to adopt and to change their pricing for this because of the fundamental economies of energy. And this just means the market is so fundamentally different that when we get quantum compute starting to turn on for each of these different tranches of application and outperform classical, there's no way for the classical market to change and adopt. This is a real classical disruptive innovation cycle. And that's ultimately what really makes me so excited about this market. It's not a question of if, it is just a question of when each of these different market factors get adopted.
Right. But one thing that I argue, in the terms of exponential progress and anticipating future, and I did that back in 2019 when it comes to the GPT moment, and I'm thinking, reflecting on the same now and how to scale the chat DNA moment, right? How you could use, the nature and other structures. But the same, I would argue, applies for energy. So one of the arguments that I have put out and caused a lot of, controversial discussion is that I believe that in the next, let's say 12 to 15 years, maybe even 10 years, there will be an abundance of energy due to the fact that we will have progress coming out of quantum computing, and we will find new material design and figure out how to have storage and distribution. So at least the marginal cost of energy will plunge towards zero. So the whole aspect of, time, the space asset, and also the conventional. But so when we look at the scaling scenario, one is we go from scale compute, but we anticipate fixed energy cost, right? So how would you think about this in the sense of having abundance to energy? Or do you think that is like an illusionary statement?
I think that's an illusionary statement. Or rather, we're talking not just an order of magnitude in energy cost. I think saying over the next decade, we can find a way to reduce energy costs by an order of magnitude, I think that's optimistic, but borderline feasible. But when you look at the energy gap between classical and quantum compute, you're talking factors of millions to billions. So just thermodynamically, you end up in this regime where it's very hard to imagine how we could change that. But what I do think is that quantum computing is going to be the answer to some of these problems. Another way of saying that is if you look at it right now and look at the scaling people are predicting for AI workloads and what this requires from data centers and people trying to preemptively work on, buy your data center and get a free, small modular nuclear reactor or something like this. When you just look at this, it clearly looks unsustainable. And I think, in 10, 20 years, we'll look back at this as people, trying to breed faster horses when the car was coming. Like ultimately, the energy economics of AI doesn't work. You can just extrapolate it forward dumbly and say, well, clearly something has to change. We can't just assume it scales like this.
Right.
And one of the big factors on that is quantum computing, since we can do so much more with so much less energy.
But even if the abundance of, or basically the marginal cost of energy, the next kilowatt hour plunges towards zero, that would just, again, that was basically where I was trying to go with this.
That's right. It has to plunge millions to billions of times closer towards zero.
Yeah, but my argument was basically saying that just increases the advantage of quantum computing, right? Because there is an energy reduction cost for conventional compute, but that would also apply for quantum computers. So
that's right. Ultimately, with quantum computers, the energy you need to run them isn't a thing that factors in the operating plan.
Right.
Costs, right? So you just don't need to think about energy costs for quantum. Anyway, you need to for classical. Until you're really starting to squeeze the juice out at which point quantum is already the default compute modality for large-scale data workloads.
Right. But there's also a lot of arguments that you say that what are the actual economic use cases? So do we need quantum compute for a lot of the tasks that we are doing? Where do you see the near-term big business use cases coming out of quantum computing?
So I think when you look across the world of what we use high-performance compute for, you can see some applications, databases, data storage, data crunching, where quantum computers don't look like a great application for. But when you actually then look at what you spend the most compute cycles on, you see problems like optimization, complex optimization, portfolio optimization. You see things like simulating complex interactions at the center of a drug molecule. And a lot of these look like applications we can solve efficiently with quantum computers. So ultimately, when you start dissecting the market and say, what can quantum do and really have a value add on in the near term, you typically look at these kind of hybrid applications where you take the workload you can efficiently do on your classical computer already. You say, great, I'll do that on my classical computer. And then you can distill down a really core nub of the problem that you can only run on a quantum computer and then run that thing on a quantum computer. And definitely, in the near term, and by that I mean the next 5 to 10 years, there's a very clearly harmonious partnership between the stuff a classical computer do and the stuff a quantum computer do. Ultimately, if you look at this, in the big picture, classical computers have existed 70 years longer than quantum computers. So problems that you can already do pretty well on a classical computer, you carry on doing on a classical computer. The really interesting workloads for quantum computers aren't things that we already do on computers. The things where we currently have people in labs, running tests, testing out chemicals in a test tube, iteratively measuring them, or building out, battery and testing battery chemistries because they can't model these things on computers. It's those marginal, interesting extra workloads, which you can take from someone in a lab to something that runs on a computer. Those are the really interesting applications that we start seeing value unlock earliest on.
So that's the efficiency part. What do you think about actual creation? So where do you look like time-wise? If you have some kind of quantum computer running a quantum AI algorithm, some kind of foundation models or world models that are operating that could actually create something new. So this, for the sake of the argument, in terms of material science, we would actually create some new elements that would literally revolutionize how we create batteries, some extending the periodic system by 5 to 10 new elements coming out of something that is a computational creationalism, if you like, disruptive creation. When do you think that could happen? Do you see that at all? Or is any creation optimization within a given?
I think ultimately, with all these things, people have dreamed of lots of these different actions, right? The challenge isn't having some human creative drive saying, what if, what would this look like? The challenge then becomes the computational power to go from this could be really interesting to how do you take it from a hypothetical to something you can actually crunch and actually test out. And those kind of problems end up being bottlenecked typically on compute.
So what you're saying,
I wouldn't view this as a different class of problems. I would just view that as having a sufficient abundance of compute. You can go daydream rather than being limited to the problems that you're already close enough to solving to just be cranking the handle on.
All right, so you would see variables or pattern recognition that human has not seen within a big computational mass of data, that you would find other patterns to build new relations of substances that are created together. So it's basically creation, innovation, pack knowledge, do more with less, kind of sort of like an action economy that you create things within a given data set. That's basically the part of creation that you look at then, right?
I think that's a fair assessment. Ultimately, take chemistry, for example. We understand chemistry really well at the big picture. And the really interesting aspects aren't can we find new elements? We know where these are. We know what they are. It's can you find efficient ways of making things economically affordable or energetically affordable that we couldn't otherwise? Or can we find a way of modeling some detailed interaction at some transition metal, element in some biomolecule, so that rather than having to do a lot of extensive tests to work out how it works, we can massively reduce the number of tests we have to run in a wet lab to do this by having already ruled a lot of these out in simulations. And it's this really big multiplicative effort that we get. It's not replacing humans. It's not replacing classical compute even. But it's just adding another weapon to the arsenal that allows us to crunch data sets and problems that we can't any other way.
Okay, but now you're saying, and now we're getting in a section where we drift a little bit off into your personal belief and philosophical reflections on this journey, right? So if you're saying that there's a given, a chemistry or a solvable domain where we have a totality, so basically the physicalism is to get better explanation of the world as it operates. Do you see limitations of that? Because you talked about replacing humans, right? So are there strict limitations to what a quote unquote quantum AI cannot replace? Or are there not any boundaries of things that given a mechanical humanoid with a quantum AI could, take over? So where are the boundaries of not replacing humans?
That is a very big question. I think ultimately we can debate, some of the philosophy behind this, or just look at what we've seen over the last few decades. And I think I have a firm belief, first of all, that with any technology, the killer application, the real big deal, takes a while to be discovered, and you only learn in retrospect. So I think with all the stuff we've been talking about, a lot of the problems we've been talking about are broadly safe returns, right? Something where you can say, we can right now work out what we can do with our quantum computers or our hybrid classical quantum computers, training AI models and things like this, where we can say, we can generate value with this and we understand how to estimate the value creation. I think when you really start dreaming big, you start looking at the unknown unknowns, the killer applications. And history tells us that these killer applications are only really properly understood in retrospect. If you look at people building the first computers back in the 1960s, they were used for, handling bank ledgers, handling HR systems, built for doing Monte Carlo models of, neutrons moving through atomic bomb structures. They were essentially doing very safe problems we could do by hand and just saying, we could do this problem by hand, and now we're going to do it 1,000 times faster on a computer. These were very clearly valuable problems, but no one would have predicted the internet or the economic value that's been created by, the software industry. When we look at quantum computing, we can look at the known unknowns, the problems we want to solve that we think we can estimate right now, what size computer we want to solve them on. But the really interesting economic value and the really interesting kind of business value comes from the stuff we can't fully understand. Not because we couldn't do the analysis right now, but because it's just not obvious to us what we're going to be able to do when we put all these different aspects together with the problems we're facing as a society at that point in time. So I don't like to believe there's any hard boundaries in any of this. The boundary really becomes our ability to understand where these problems are and how we best apply them to really make the best improvement to society.
So you're applying some kind of human agency through the task of progress and creation then. So you don't see a quantum AI capable of taking over that creation.
So I think I'm a pragmatist in this, in that I wouldn't ever say ever. Ultimately, I believe consciousness is a chemical construct. Another way of saying that is anything that happens in a brain, in a human, you can simulate with the computers since we understand how to simulate chemistry. And there's an incredible amount of emerging complexity out of these large complex systems, just like there is in a computer, in a large language model. So I don't think there's anything fundamentally inherent there, but pragmatically, I think any system with humans in the loop has a lot more flexibility than a simple program model. Not for any fundamental reason, but just because humans are pretty awesome at what we do. And the challenge is mostly giving people longer levers than it is trying to find ways to take them out of the loop.
I like to romanticize about the human species, and I like to have that we're pretty amazing. But then the question always pops in, is it relevant? So, you could think about consciousness as a chemical process. We could see we hack biology, we hack chemistry, we figure out, to how to program a conscious entity. But the sense of agency, the experience of your own experience, what it feels like to be talking to you, it kind of sort of seems like something that is fundamentally profound and important to human beings. But then also you can argue that if you take it out of the loop, there is no observer. So we would see some kind of philosophical zombie state of a perfect AI walking about, could do the same things without having that experience. So two questions, I guess. So is then consciousness something that we will figure out computationally? And if so, what distinguishes us then from a robot in future? And if it's not to be figured out, what does that leave for humans like to ponder?
So now we are getting into the big philosophical point.
I always end with that, and especially with smart brains like yourself.
I would say I don't think there's anything fundamental about humans. What separates a human from a monkey or a human from a pig in terms of our lived experience? Fundamentally, I just don't think there's that much. What separates a human from a perfect electronic simulation of a human? I don't think anything. I think you can get into kind of accounting, bookkeeping details about how you define the differences. But I really fundamentally don't believe there's anything unique about the human experience versus any other complex system. I think it's a very egocentric view to believe there's something uniquely special about humans versus an AI model that's sufficiently complex, or from a monkey or a pig.
So that is also the risk that we ponder. So I recently written 2 books with a quantum physicist friend of mine. One was trying to prove that we are not living in a simulation, which turns out to be a very difficult task. And the second book is what we call the singularity paradox, bridging the gap between humanity and AI. And here, the argument is basically to say that, just like you just said, if there is nothing special, outside of some kind of physical, mathematical understanding, then, there is a risk of externalizing authorities and giving everything on to algorithms. Because then you are like using a tool, a hammer, you are not experiencing the hammer until it breaks, right? The Heidegger wrote about Sein, about, the Lebendigkeit, what it feels like to be alive. So when you then offload all these authorities and tasks to super efficient AIs, you take away the agency. And then we become like monkeys or ants to that super intelligence. So creating that artificial general intelligence, we think, is a very, very dangerous endeavor. So we came up with what we call artificial human intelligence. So we start with that conscious human experience and we romanticize about what it feels like to be a human. And then we hack biology and chemistry and build biological weapons.
I would disagree that this is a problem that's unique to an AGI, right? We've seen plenty of human-led regimes that have done terrible things and that have led to people following orders and doing awful things because they don't see the full big picture of this. And ultimately, this becomes a structural problem in how you reward and incentivize and structure a society in much the same way as you can build, evil authoritarian regimes. You can also build an evil authoritarian AGI. I don't see there's anything fundamentally different between building human structures that reward the right behavior versus building computational structures that reward the right behavior.
As long as there is a definition of right behavior in someone experiencing right or wrong. So if you look at, take an example, like Google's AlphaZero, right? So your chess engine, human best chess engine is built on Stockfish, and we have all this, understanding of the game of chess. And then AlphaZero plays against itself, and it plays some kind of weird moves that get adapted by the chess players, where we don't understand why these particular moves win, because it's very, very controversial and it's against, our understanding of theory. And that reward mechanism in an AI is to say there is a binary win-lose. If there's a trade-off of right and wrong, we could anticipate a right scenario or right behavior, but we could potentially, because we don't understand the underlying mechanism of the complexity of the process data, we cannot error correct. So, Gorbachev did not press the red button back in the 80s because he knew that a nuclear war would be a destruction for humanity. And you could argue the opposite with AI, to say we are striving for efficiency and optimization, but we're not seeing the implication because we're not seeing the risk of a potential scenario like that. Is that something you can relate to, or is it just...
Yeah, but I think that all comes down to making sure you have the right cost function and you ask for the right thing. I think that's exactly the same with humanity. A lot of, when you raise a child, a lot of what you teach a child is to understand, that winning a game isn't everything. To understand that nature isn't binary, that you're playing a long-term and infinite game, not a zero-sum game. And the same thing is true with any sort of computational model. Making sure you are truly understanding what problem you're trying to solve rather than just solving a poor simulacrum of the problem.
Yeah, and I agree with that. And I'm a big, I was very inspired by David Deutsch, Beginning of Infinity, and thinking about, the infinite potentiality for better explanations, and creating better problems, as I use in the terms. And I'm a very strong believer in that. And therefore, I think that instead of creating AGI and staying, stupid monkeys, I think the much more promising path to understand, to be able to build those underlying initial conditions for optimization. I think, building an AHI, an artificial human intelligence. So whatever we are or are not, what we cannot take away is that self-perception, the agency. And I think not that it's given that the agency is necessarily there. So obviously we could have the argument, we build a brain, 83 billion neurons, and whoops, we have consciousness. But you could also say, I build an identical brain without consciousness, because we don't know. We simply don't know. So you could think about a scenario where the lights go off. So I would behave in the exact way because the whole data processing is perfect. So you would not recognize it. You would not distinguish me from a conscious being. So I could say, hey, Chris, are you conscious? And you would say, yeah, sure, I'm conscious. And you say, Anders, are you conscious? And I said, my initials are AI, but I'm sure it's not conscious, but you would never know, you never know in the subjectivity. So this is why we thought, when you think about the whole aspect of upgrading a human in order to cope with that complexity.
Yeah, these are fascinating questions to ask.
But you don't resonate with that. You think you're a hardcore physicalist and think we can figure it out.
Yeah, I believe we fundamentally understand the laws of physics and that everything else is emergent behavior. And that just because emergent behavior is very complex doesn't mean there's something unique about humanity.
So that then you say that eventually we will surely could argue that we know that a robot would be conscious because we would fundamentally understand the chemical process of consciousness.
I don't think there's anything fundamentally special about the chemical process of consciousness. And I think it's a very human-centric point of view to believe out of our chemical mess there's something truly unique.
So, but then again, do you believe that we will have a robot where we could say this robot is conscious, it's a sentient, AGI, whatever you want to call it, and we know for a fact because we have understood the process or the creation of it?
I think knowing for a fact, speaking as a scientist, is a very strong statement to make. But yes, I think we'll get to the point where we have to be very careful with how we define this, because in all the behaviors we see things that are consistent with what we'd expect.
That's such a beautiful clarity on a vision of a future. And at the same time, I sense your positivism, your possibilism of a positive future. And I always think that this argument is very appealing to me, and I resonate with that. But then I say, don't we then risk, in our simple terms, if we don't merge with technology to that extent, that we are kind of sort of the ants to that super being? Aren't we quote unquote creating a Deus ex machina, God out of a machine, and we become the servant of a potential super intelligence? How do we stay in that control or just have that security then if we have created an artificial general intelligence that has a sentience, that had a consciousness like our own?
I think we're putting a lot of faith in technology under that model and technology to advance far faster than I think it's going to. I think we will have plenty of time to be debating the meaning of this and what safeguards we put in place and what does this look like over the time. I don't think, like any technology, this is going to be a light switch moment. And I think right now, especially with AI, we're seeing a lot of progress and have been seeing a lot of progress over the last few years, but we're now also starting to understand just how much progress we need to get to a full AGI situation. So I don't think this is something we need to worry about too much as a binary light switch moment versus as a slow climb up a hill where we slowly start to learn how we best use this technology.
So it's not a slow boiling of the frog. It's something like this. No, but it's beautiful because this is unlike many of colleagues of yours and engineers and some technologists that have a different view on this. And they think that a technological singularity or an AGI has that potential moment that we cannot foresee and cannot understand. And then it just skyrockets or snowballs into some kind of hyper efficiency of an AGI, that an AI optimizes itself beyond our control. So it's very promising to listen to you with that deep fundamental understanding of what you're doing, obviously, to have that belief system in place and to have the values also to shape beneficial artificial general intelligence or artificial intelligence based in on a quantum computer. So that's very promising to me. I like to go down, each path down rabbit holes and then play with it. So therefore, I just, also wanted to get your take on it. And thank you so much for sharing your reflections on that. I hope that we are not a homo obsoletus that is not needed for any particular reason, and that we have that conscious experience. But if you look at like how society is evolving, you could also argue that a lot of people are getting detached, looking more like philosophical zombies being dragged through life through dopamine and serotonin and endorphins. So are there any scenarios where you'll have a dystopian negative look at the future?
I am in general an optimist and believe that humanity will find a way through, and as we always have done, find a way to prosper. This doesn't happen for free. It requires a lot of effort from a lot of different people. But fundamentally, that drive is there in humanity to make the best and find the right way to use these new tools we find ourselves with. And historically, there have been many people, over thousands of years saying, well, the children of this generation are lazy and ignorant. And we've never seen this slow us down for more than, small pockets of misdirection. So I'm an optimist that humanity will find a way to become better and stronger as it has done over the last thousands of generations.
I think that's a beautiful way to wrap it up, Chris. I really much enjoy this conversation and thank you for coming on and sharing your insights. I've learned a lot again today. And it's beautiful to have people with good values in place and to look for collaboration and still strive for progress and try to lead, but also not in a sense of, using technology and winning the game in a binary sense, but to actually improve the state of humanities. And thank you for pushing that and for being a lighthouse in that drive. And I hope that together with IonQ that you guys can be a leader, a visionary driver of this very promising technology.
It's been a pleasure, Anders. Bye-bye.